Hello, everyone. I'm not Allison, as you may notice, but I'm Beatrice, and I will be doing this interview today with David while Allison is traveling. So, welcome to the Existential Hope group this Friday. Um, we're here today with David Leigh, who's a scientist, and he works with molecular machines. He designs and synthesizes molecular models and machines, and he works at the University of Manchester. And as I'm not an expert in the field of nanotechnology, I don't know exactly how, but I am aware that he's made a lot of contributions to the field of nanotechnology. And I've heard that he's really someone who's supporting a lot of junior scientists in the field and really making like a pioneer for in the field of nanotech. Um, and I understand also that um, he has won the Feynman Prize in 2007, I believe, from the Foresight Institute. And really, I'm excited to hear from David how the work that he's doing with nanotech can really help create futures of existential hope. And hopefully, this interview will be able to, inspire more people to get curious about what's happening in the field of nanotechnology and the potential and the possibilities of this science. And I know that David is doing a lot of work also popularizing and explaining the work of his field already. I saw the Nanobot video on YouTube. Uh, so I'll paste that in the chat as well. Um, yeah, it's a very illustrative recommendation if you're curious about how nanobots are made. Yeah, so I think let's just get started. Thank you so much for coming, David. What?
Thank you, Beatrice, and welcome everyone.
Yeah, thank you. Well, okay. So, David, what are you working on, and what got you started in this field?
So I'm a chemist, a synthetic chemist at the University of Manchester in the UK, and we work in the ultimate in miniaturization of technology, molecular machines, trying to make artificial molecular machines. And the reason that we know that an artificial molecular nanotechnology is possible is because there already is a working molecular nanotechnology, and it's called biology. And that's the reason why scientists at the start of the 21st century, or one of the reasons why we should perhaps be interested in trying to make molecular machines, it's because biology uses molecular machine for everything. Every conceivable biological process depends on molecular machinery, the way that energy is harvested from the sun, the way that it's stored in the cell, the way that we can think, the way that we can move, the way that you can process what I'm saying, all depends upon controlled molecular motion and molecular machinery. And in contrast, humankind at the start of the 21st century, despite our myriad of fantastic technologies, we don't use molecular machines for anything at all. So every catalyst, every reagent, every polymer, every pharmaceutical, every material just relies upon the static properties of those materials for their functions. Biology hasn't evolved over 2.5 billion years to use molecular nanotechnology for everything for no good reason. And when we learn how to do the same, how to control molecular level movement, I'm convinced it will change all aspects of functional molecule and material design. It will make things today look like a Harry Potter film. And I got into this area by chance. We were working on something else about 25 years ago. We were trying to make molecules that would bind to carbon dioxide and capture, sequester carbon dioxide from the atmosphere. And one of the molecules that we were making was a ring type molecule. And the idea it would bind CO2 in the cavity. But when we tried to make it, we didn't get a single ring at all. What we actually got were two rings interlocked together, just because of some of the quirkiness of the chemistry. But we recognized, in fact, following on from some of the other earlier pioneers in the field, that having these interlocked architectures, if we could control the movement of the components in that, maybe we could use those large amplitude motions at the nanoscale to make molecular machines. Because the big problem in the area of trying to do this is that you can't shrink engineering concepts from the big world down to the very small, because the way that matter behaves at different length scales is just so different. So my mobile phone is just going to sit on the desk in front of me because it's a big object. So it's an object in the big world. So it's got inertia, and it's not going to move unless I give it some kinetic energy. But if this was a molecular sized object, it'd be constantly moving through random thermal motion, through Brownian motion. So basically you have to design molecular machines in a completely different way to how you design machines in the big world. And so what we really do is we're learning how to do molecular engineering.
Yeah, that's extremely fascinating to hear. I I mean, you told us it could be like Harry Potter, and one thing we're really trying to do with this podcast is to like try to inspire young people to think about what's possible. So if you tell us, even is there anything more specifically you can say, like what are the possibilities of nanotechnology?
Well, let's just say I think that just that look at materials. I think that they will become active. We will have active matter going forward. So things like clothes will not just be made out of fabrics. Won't just be made out of fabrics that just have one shape and one size. You'll be able to make active clothes that shrink to fit every wearer, or their surface properties can change to repel viruses, or to be sticky when they need to be, to change color. Just like you could clear up the icons on your desktop by clicking a button, and they'll all go from being randomly distributed to all being in order. One day you'll be able to go into your kid's bedroom and see all the clothes all over the floor, click a switch, or say, Siri, put those clothes away, and lasers will come out of the roof, and the active materials will know where to jump back onto the hangers after they've first got rid of all the dirt and sweat on themselves by just being able to repel those sorts of fabrics and iron themselves automatically. All that, I mean, that's just a trivial example using fabrics. But really, I think we're at the start of, in the field of synthetic molecular machinery and this type of molecular engineering. It's a little bit like being at the where Stone Age man and woman had just invented the wheel, maybe to grind corn or something, and they couldn't foresee that putting two wheels on an axle would enable you to control movement and still and carry things more, transport things more easily, and still less would they be able to predict that you would one day be able to power things and be able to make motor cars or and foresee cities. So it's a little bit like we're right at the start of this process, but what we have that Stone Age man didn't have is that Stone Age man didn't have a technology that they could look towards, whereas we have a working molecular nanotechnology called biology, and so we can see all the absolutely amazing things that biology is able to create, all using just 20 building blocks, the amino acids. Whereas we've got the whole of the periodic table, the whole of 150 years of chemistry and physics that we've developed. And when we apply all those things in ways that nature doesn't need to do, it hasn't needed to do through evolution, as I say, things are going to be unimaginably different. I truly believe that. It's going to take a little bit of time. It's not going to be immediate. And it's really hard to predict exactly what that future is going to be. But that's precisely why we want to invent it.
Yeah, I'm curious as well because nanotechnology doesn't seem like a field that's been around for that long. But since you came into it, has there been any um what's the development been? Has there been any shifts or changes?
Yeah, of course, nanotechnology means a lot of different things to different people. So, but just to talk about my particular area of synthetic molecular machinery, It's actually something that Feynman touched upon in his famous lecture, There's Plenty of Room at the Bottom, where he talked about the possibility of little molecular robots being able to assemble objects by moving atoms around. And that's, of course, a vision that Eric Drexler seized upon for his molecular assemblers. And but I think that it was difficult for people to move in that direction for a long time because uh, I think that the way to do it is through mimicking how biology does engineering, not to shrink down macroscopic engineering concepts, as some have interpreted the Drexler type of way of doing mechano synthesis, say. Whereas we know how biology does things. And I think being able to mimic those processes using chemistry and physics makes an awful lot more sense to me as a practicing sort of synthetic scientist. So the big developments that have come came really in at the start of the 1990s when Fraser Stoddart and a chemist now at Northwestern University, and Jean-Pierre Sauvage, now an emeritus professor at Strasbourg, and Ben Feringa at the end of the 1990s in Groningen, realized that you could maybe start to make molecular machinery. And they made mainly switches, and they were awarded the Nobel Prize for Chemistry for this pioneering work in 2016. Ben also serendipitously formed the first synthetic molecular motor, but the way that works didn't really explain how other sort of motors and machines could be made. It was sort of really a fancy switch. And so our contributions and those of others coming after those pioneers has been to recognize how to take other facets of what biology does, so-called ratchet mechanisms, and to take the next sort of step to make more sophisticated machines. So I think that that early work from that trio was extremely important for exciting chemists in particular to think that they could enter that area. And then other advances in theoretical physics have shown us how we can actually make mechanisms that we can then apply to molecules, which people like myself do, to make much more advanced systems than were possible before.
Amazing. Is there anything that you think is currently going undervalued within the field?
Yeah, there's a lot that's science is always like that, that things take time to be recognized. And I think also um, the most important way to get advanced in science is to take discoveries from one area and apply them in a completely different area. And those things take time to have that kind of crossover because it's not easy to recognize why some discovery, some profound finding in one area it can be applied in another, because languages within science are just so different. It's not so easy to cross over some of these concepts because science is so complex. But again, one of the things I'm most proud of that our group have done is take concepts that came from theoretical physicists about how to control the movement of Brownian particles, so just pollen grains moving on randomly around on the surface of water. That random thermal movement, theoretical physicists realized there were ways to directionally control that movement. And we realized that because molecules are also undergoing random thermal movement, if we just took those ideas that the physicists had applied to Brownian particles and applied them to molecular machine design, it would be a way of making motors. And in fact, it turns out it's even more profound than that. There's applications of those sorts of mechanisms far beyond even molecular machinery. And I think it's actually the key for how chemistry becomes biology, how the inanimate becomes animate. And so, I think that's going to be a really exciting area for the next 10, 15 years as people show how physics and chemistry actually become biology. I don't think biology is really, really complex because of the way that evolution works. And I think that it doesn't have to be.
Yeah. And it's very, very interesting to hear. I was also hoping that you would be able to provide some light on what it's basically, if we're trying to, inspire young people to come into this field. What is it like to be? What's it in the life of your as a specialist in your field?
Well, the field is extremely exciting. It's not a mature field at all. So there's plenty of discoveries to be made. It's like a little bit like being like an explorer in the 1500s, knowing that there's being like Columbus sitting there in Spain, knowing that he wants to go towards India, but it's a long way round to go east. So he goes out to the west. He's not afraid to lose sight of the shore. He knows that there's this vision of something great there, but in fact, he discovers something even better along the way. And if you're willing to lose sight of the shore and go off and explore things, then there's lots of exciting things to discover because this is not a mature field at all. There's lots of exciting things to do. So, what's my personal day like? Well, like lots of people, I guess one of the nice things about my job is that every day is pretty different. So today I'm speaking to you from lovely British Columbia. I'm over here doing a lecture tour of three of the universities here today at the University of Victoria. Earlier in the week, I was at UBC and Simon Fraser. So I get to speak about the great work the work that my great students and creative students are doing. Um, Normally, I go into the laboratory to see my group only once a week when I'm back home because I tend to work from home because I'm the rest of the time because I'm writing or unfortunately responding to emails, which take up a lot of the time. But when I'm in the lab with them, we start off with our group meeting. So that'll be an hour of people giving the latest updates to everyone in our team of 25, 30 people. And then I'll have different meetings talking to other members of the group. We'll have project updates. And I won't write anything when I'm actually at work. And I won't respond to emails. I'll just be meeting with people. But that's only one day a week, and the rest of the days are sort of, um, yeah, thinking a lot as well. Actually, that's one of the luxuries of what I'm able to do, because I need to prioritize the projects within our group. What's great and what's not ready to be discovered yet, and also trying to find what things from other fields that we can bring into ours to make our machines better, or to take our machines and concepts and how can they be applied in different areas.
Yeah, you're making it sound very exciting and like a very exciting field to get into for sure. Um, so I wanted to if we continue on this slightly philosophical lens, um, the premise of this whole group is to think about what's the direction we want to take this in. So a little bit like the Columbus metaphor that you were speaking on, and to think what do we want for our society and not just what don't we want. So if we speak of existential hope, and we think about that in terms of what the long term future will look like and how we can make that um, a good place. So, what I wanted to ask you is, do you have a vision of existential hope rather than existential angst for the future?
Yeah, I'm definitely an optimist about the future. I just see how technology and society has advanced for the better over my lifetime. Obviously, with blips along the way, but I think that we are the quality of life, at least for most of us in the West, is way better than it was when I was a young boy. Um, but in terms of my vision for the future, in terms of science, helping that and helping society, is again to say that miniaturization of technology has always advanced technologies dramatically, and it has inherent amazing advantages. So miniaturization means that you need less materials, both to build whatever it is that you're building, less waste is produced, less energy is required to run it. Uh, 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 there are, it allows you, miniaturization allows you to have new functions and new applications that are simply not possible with large things. So these things address directly the sustainability and technological desires of society. So I think that they are really key to a future where we a much more sustainable future where we don't need as much energy or it's used more wisely because of these technologies. So the miniaturization of technology is just an inherent good. It's an absolute good for society. Of course, things can always be used for bad. And if you see the latest James Bond film, he has a few problems with nanobots. But we shouldn't let that worry us. I'm sure that those are, at least from my lab, those are a long, long way off yet. Um, and technology can always be used for bad or for good, but it's the increase in knowledge and the miniaturization of technology is certainly just an inherent good.
Yeah, yeah. Actually, one of the questions that we usually ask is that it always seems very hard for people to envision the positive scenarios, and envisioning dystopias is easier, because there are so many ways that things can go wrong, but envisioning something like utopia is much harder, and often when we do, it ends up seeming eerie or absurd, and we have a harder time agreeing on what we want maybe than what we don't want. But is there anything you think that we can do to change this?
Um, I don't think that that's my role. I'm not a I wouldn't claim to have a great vision of those sorts of things. I think that those are societal and political questions about how we want to live through the advantages that nanotechnology, molecular nanotechnology, will give us. Uh, but my uh, what we are doing in what my vision is to try and get there as quickly as possible, because I completely see that it's going to give all these kinds of advantages for sustainability. I say using less waste, less requirements for energy, technological advances and new functions. It's hard to see what those will be. And of course, those will definitely raise societal questions about um, uh, what people are going to do if they have less work that they have to do, if we don't need to mine so much materials, if there's much more automation in our society. Of course, that will mean that our society will change, but I leave it for others to think about those things. I don't think that my views on that um, are certainly not as well. I'm not as well informed on that as I am on the potentials of nanotechnology and how to get there.
Yeah, I w- from your vantage point, are there any undervalued risks though that you see that we need to get around to solving?
I definitely don't think that self-replicating grey goo or anything like that is any kind of problem at all. By there are dangers of the dangers in sort of that side come from synthetic biology, which is sort of taking existing biological pieces and using techniques like CRISPR to chop them up and to be able to manipulate organisms to have bad things associated with them. So those sorts of technologies, those are removed from what I do. And those are very powerful current technologies that, in the wrong hands, I'm sure could be used to do bad. But I'm not sure that they're under that those risks are known to people working in that area. I think that they are known, but we certainly shouldn't uh, make things like grey goo and things like that as comparable risks. The chances of anything like grey goo happening based on synthetic molecular machinery is it's infinitely small, and we're not in any position to do that, and we won't be for hundreds and hundreds of years.
I've heard of the concept of grey goo, but do you want to just explain it briefly?
Well, grey goo is one of the Eric Drexler came up with this very interesting idea of molecular assemblers, and those are things that we in our group kind of do work on or we call it molecular robotics, but these are molecules that can be programmed to build other molecules. They can't build anything sophisticated yet. They can't build themselves. Nothing like that. But we're going through the very early stages of being able to do that. And actually, there are examples of that. That's how biology works as well. There are things called super enzyme complexes that actually pass building blocks from active site to active site and certain enzyme super enzyme classes to build molecules. So so those sorts of things with synthetic molecular machinery have good analogies in biology. But when Eric came up with this concept, the idea of grey goo came up, which could be you could have self-replicating nanobots, which would just be able to pluck the building blocks they needed from almost any kind of matter, make more and more of themselves and replicate in the way that bacteria do. But these things would be able to feed off essentially anything. And they're popularized in things like a Crichton novel and other sorts of things. But those are not serious risks in the field of nanotechnology, not in the time, not on an imaginable time frame for science, whereas there are real existential risks in other kinds of synthetic biology if they were used for ill. For example, putting plague into viruses or something, or not viruses, but into bacteria that could proliferate. No, but those risks are known, and those are the sorts of things that really need to be taken care of and legislated together.
Yeah, yeah. Well, it's assuring to hear that the great boom scenario isn't very likely, even though there are other things to worry about. But if we go back to the positive scenarios and envisioning those, are there any specific breakthroughs that maybe if we think like on a 5-year time frame would tell you that we're on track to getting to this more
Uh,
scenario?
I think it's hard to say what will happen in 5 or 10 years time that will really change our lives. But I mean, who would have thought that with Facebook or TikTok or Snapchat or whatever it is? When they came out, no one, only maybe Zuckerberg himself thought it could be so persuasive. But it's really hard to know how discoveries will be taken by science and what will actually be some killer app that changes society. Really hard for me to know about that. And what I can say is that the first applications of synthetic molecular machines, they're likely to be things like smart surfaces that can do stuff. So smart adhesives, so say allowing you to recover silicon chips or gold saved from silicon chips by just shining light on it so that the bits detach. And so allowing more renewable things, adding real value to conventional materials. Um, the reason I'm saying surfaces is that surfaces only require very small amounts of molecular of substances to be made. Whereas if you wanted to make factories, molecular factories that were making large amounts of something, you would need an awful lot of stuff to do that, and that would be expensive to build, but using our current technologies. There are examples of very, very simple molecular nanotechnologies already going into products. So some phone screens are strengthened through the sort of mechanically interlocked structures that I was talking about that others and ourselves discovered many, quarter of a century ago. So those are already being used to have um, to improve the properties of conventional materials, but it's going to take a little bit of time before these ideas and concepts of molecular machinery are sophisticated enough that they can do something that's that's going to be a killer app, I think.
Yeah. Is this if you think of someone new trying to come into this field, is it something in particular that you would recommend they think about specializing in?
Um, I would say that this idea of applying the concepts that turn molecular machines into motors is actually being able to use energy to then perform some task. But this isn't limited to just molecular machinery. It could be used for materials. So using energy like light energy or chemical energy or electrical energy to make materials that at the molecular level do active things. And it could be that they sense things, or it could be in a very sensitive way and respond to that. And this is an area at least into that no one has been, and people are just starting to do now, and it's much less developed than any of the other areas. Like, so taking the concepts that we and others have applied to molecular machinery and applying those sorts of concepts to materials. Some people are starting to do that now, and I think that could have really exciting um, that will definitely have really exciting consequences because it'll stop materials from just being static fixed objects, and they will be really responsive in ways, as I say, that it's hard to even imagine now. My shirt being like a computer and being able to respond to its environment, to sense things, to if it senses that there's viruses, it puts out antiviral bits on the surface, or it closes the distance between the fibers to stop it being penetrated. But when there's none around, it opens the fibers so I can breathe through it. All these kinds of things that will just happen automatically or autonomously through active materials. I think that's an area that will that people can really get into now, and they may well be able to come up with a killer app for that in a short period of time because it's right at the start.
Let's hope. Let's hope it happens soon. It sounds very like it could be very useful. So again, for someone new coming into this field, is there anything in particular that you would recommend reading, listening, watching, and it could be like fiction or non-fiction?
Well, this podcast series obviously is the way to go. I don't know, to be honest. I'm not. Uh, if it's people from if they're scientists and they're PhD, they're thinking, what do I want to do to contribute to this area through research? Then the sorts of fields to go into. Then it's good to be a specialist in something. You've got to have something to be able to offer to others. Jack of all trades who have no specific skill. I think that that's quite difficult. But at the same time, if you're a specialist, what's absolutely crucial in this kind of field is to have a broad awareness of what other fields can do, because that tells you where your expertise might be applied in a different kind of area. And so that you can specialize in chemistry, or you can specialize in physics or in molecular biology, but do something that gives you a skill of expertise. So the expertise of me and my group is in synthetic chemistry. We can build molecules, but and that gives us a big advantage over, say, physicists who may know more than me about how to design molecular machines, but they can't build them because they don't have that skill set. So my advantage over other synthetic chemists in my field is that I'm aware of what physicists know. I'm not an expert in it, but I'm able to take some of what understand and appreciate some of the things that are going on in physics or biology, and take some of those concepts and use them in the design of the things that I want to make. And I think that at least during my career, that served me very well. So be expert in something, but be very broad in your or outlook. And that goes back to what should people read. They should read lots of things. They should read Nature and Science and New Scientist and other popular science magazines to get a broad overview of what's happening, because often these journals or these outlooks feature what are exciting developments in a particular field, and it just gives you again, seeing breakthroughs in one area and transferring them to another. That is a huge skill. What distinguishes great scientists from the ordinary is three things. It's the ability to come up with a project, a project that's or a problem, identify a problem that's important enough to that you could want to work on it, but it's difficult enough that no one solved it already. And then the third thing you need to have is this uncanny ability to realize that the time is right. From developments in other fields, enough is known that now this problem, it becomes tractable, and by applying these breakthroughs from different areas.
That sounds like very, very wise advice, and um, trying to synthesize. Uh,
I should have added a fourth thing. You have to be lucky as well.
yeah, yeah. Well, that's always a factor. Um, well, okay, thank you so much. I think now I'm gonna take us on a bit of a turn again, and ask you for, in every one of these episodes, we also ask for an example of a potential catastrophe, which I'm not sure if you're familiar with the term, but it's Owen Cotton Barrett and Toby Ord at the Future of Humanity Institute, who they define the term catastrophe as an event that causes there to be much more expected value after the event than before. So basically, it's the opposite of a catastrophe. And we like to think about that and play with that in terms of, helping people envision these positive futures.
Yeah.
S- do you have any suggestions of um,
Um,
what?
yeah, I mean, of course, this could be many things, but let's say, of course, we've got this huge energy crisis in the world at the moment, and even without the war in Ukraine, um, the way that we've been using energy is catastrophic for climate change and so on. So I think that something that would be a new catastrophe, or whatever the word was, a good one would be biology actually uses chemical fuels. It harvests the energy from the sun, but all the molecular machines in your body work through chemical fuels. They use ATP converted to ADP and use the energy from that to do things. So I think something that would be a real breakthrough would be if you could find a way to do like biology uses, use chemical fuels to well, chemical energy, to find a way to use that in a very effective way to transmit it to to be able to interface it with our current technologies, so that we didn't have to rely on more conventional fuel. So a completely new way of harvesting energy. And I've no idea how people will be able to do that. I think being able to interface those sort of fueling systems with conventional technologies would be difficult, but that would be something that would solve all our energy problems. Or I mean, there are other ways. Fusion. If suddenly there was a breakthrough in that could solve the world's energy problems, that would be great. Allow us to concentrate on solving other massive problems such as clean water and many of the other sort of problems we face as a civilization.
Yeah, I love it. It's very specific. It's going to be very interesting because what we'll do is we'll ask an artist to sort of interpret this and try to create an art piece out of this prompt. And yeah, we're also aware that the word is a pretty bad one because you catastrophe and everyone just thinks about catastrophe. So we also try to find a better name for it. We actually just had a bounty where we were asking for suggestions of better names, and I think the winner is efflorescence.
Oh,
But
thanks.
if you have any better suggestions, we're also very open to hearing them. Um,
Uh,
yeah,
no, that sounds great to me.
yeah, yeah. Efflorescence is it's a beautiful one. Okay, well, I think I'll ask you. I think two more questions, and then we can go to the audience questions as well. Um, you've already given a lot of really good advice, but do you have one piece of advice that's like, this is the best advice I ever got?
Best advice I ever got was the cheapest way to pay is with money. The most valuable thing for many of us is our time, uh, and uh, and uh, when I have a big problem and I've made a mess of things, the easiest way, the cheapest way out of it is often just to pay to get it done and sorted. So, and governments could learn from this as well. Science it is the key driver of success in all economies, and all the time they try and skimp on funding it. They just need to invest properly, and they'll find that they get their money back far more than they invested. But again, it's up to people like me to convince both the politicians and the general public who vote for politicians that it's a good use of their tax dollars.
Yeah, I think that sounds like good and very concrete advice. This can be applied on a small and a grand scale. Um, Thank you. I'll go into the audience questions now. So we have one question from Machas that says, most of biology seems to work with a very small number of elements. What potential does the rest of the periodic table have for building molecular machines?
Yeah, so that's a great point, and one of the most important. So the reason that biological machines are so huge, or enzymes and motor proteins are so big in terms of number of atoms and everything, is that biology only has 20 building blocks, the amino acids, which it uses to build everything. Whereas we've got the whole of the periodic table, and we can make things that are much simpler and much more effective in our own way by using different elements. And so that's just chemistry. Um, uh, the whole field of chemistry is about using different elements and different chemistries and different conditions to achieve different outcomes. And it allows things the different elements allow you to do things that just can't be done with carbon, hydrogen, and oxygen. So that you have redox properties of metals and so on that are used in tiny amounts in biology because it just needs to do it. But we can uh, use those in a much more effective way than biology can, because biology just chooses things through evolutionary pathways, whatever works. But we can, by learning how biology does things, it gives us clues. of how to do things, we can find much simpler ways of our own of doing them.
Another audience question is, how would you deliver energy to the smart fabric that you mentioned earlier?
There could be light or electricity or maybe chemical energy in some kind of way. Even mechano energy, even the movements that you make, those could be harvested and converted into electricity, of course, through piezoelectric type of effects. So any of those sorts of things could be used in principle, I guess.
Interesting. And another audience question is, do you see any value in design rules that let engineers make design shapes out of protein blocks?
Um, Um, yeah, I don't see. It's always. I think that there's always interesting. It's hard to know what new ideas are going to, new concepts are going to be useful for. So, but just the ability to do that sounds to me like it would be extremely interesting because it's like controlling the quaternary structure of proteins. For proteins, you've got primary structure, which is the sequence, secondary structure, tertiary structure, which is sort of the folds and the overall shape. And then quaternary structure is how they stick together to form a larger object. So it sounds to me like the question is finding a new way to control quaternary structure of protein. And I'm sure that that can be useful for function. It certainly is in biology.
I trust you on this. Yeah. Another question is, can nanobots be used for atomic precision in construction of novel materials?
Yeah, ultimately, I think yes, and that's some of the work that we've done is making these first programmable um, synthetic molecular robots that are DNA nanotechnology, so that can just do simple chemical reactions to build selectively one of four different molecules. So as that becomes more and more sophisticated, that we'll be able to build more and more complicated structures. It's like having a Lego set, and at the moment or a Meccano set, and we can just use it to um, move the arm between two sites, and so pick up one thing and put it down. You need to be able to make more complicated systems and find this way of molecularly engineering those components together so they do more than the sum of their parts. And that's how complex machinery is made. But as I say, you can't just shrink down the machinery concepts that you used for engineering the machines in the big world. We've got to invent our own ways of doing that. Um, and the great thing is that we can learn by seeing how biology does similar things, and also just come up with use our own imaginations and creativity to find those rules ourselves.
Yeah, it's been it's very interesting to hear, and you're very good at making these metaphors, and I feel like I this has been a really good intro to molecular machines. I think um, the last questions I'll ask you is just if there's um, anything you think I've missed asking or anything else you want to touch on.
You've covered everything so well, Beatrice. Thanks for giving me the opportunity to speak to the group, and yeah, and thanks for asking such nice questions, both them and you.
Thank you. If you're fine with it, I think we just received one last question, which says, might nanobots lead the way from the bottom in exploring emergent phenomena in foundational physics?
Yeah. So just as we learn from physics, and we use the physics to design our molecules. Absolutely, what we do can feed back into making better theory because physics normally treats things as points or spheres, particles as points or spheres or something, and so it's uh, 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 very simplistic in those sorts of the way that it interprets or it comes up with its models. Whereas we work with real molecules, which have real shapes and limits on bond angles and bond lengths and things like this. And that gives us, in turn, gives us insights by knowing how these things that we design behave according to the physics theory. They allow us to say to physicists, well, actually, that particle that you've got on an unsymmetrical surface, you can actually achieve the same thing by having an unsymmetrical particle on a symmetrical surface. And it's something that you wouldn't necessarily think about in physics. So but using those designs to feed into chemistry allows us to make effectively, we make the molecular structures of Gedanken experiments. And then having made those Gedanken, those real models of the work of the Gedanken experiments, those can be fed back into the theory and lead to insights into the theory, how it applies in different ways. So it's definitely a two-way street, I think. I hope so anyway.
Yeah, yeah. I think that was a good last question. I'm happy we got it in, and it really shows this importance of, which is a big part of what we're trying to do at Foresight. It's this cross silo collaboration between the fields of technology and science. Well, again, thank you so much, David. It's been really really interesting, and thank you everyone else for joining.
Thanks for having me. Bye all. Take care. Stay safe.